You clicked this video because you want to know whether to use supervised fine-tuning or reinforcement learning for reasoning models. The real problem is that most engineers treat this as an algorithmic choice when it is actually a hardware efficiency constraint. By the end of this explanation, you will understand why skipping one phase can save your GPU memory and force better batch sizing strategies than the traditional pipeline ever could. When we talk about training large language models for reasoning tasks like complex math or logical deduction, there are two main paths everyone discusses. The first is supervised fine-tuning, where you feed the model examples of perfect steps to mimic. The second is reinforcement learning, which rewards the model based on whether it gets the right final answer regardless of how many intermediate steps it took. For years, the standard industry practice has been a sequential pipeline called SFT, then RL. You train with supervised fine-tuning first to get the format and basic logic down, and then you run reinforcement learning to refine the reasoning capabilities. This approach feels logical because it mirrors human learning, where we study before we test ourselves on exams. However, recent investigations into models like R1 reveal a hidden cost that turns this algorithmic decision into a physical bottleneck for your hardware infrastructure. The core issue emerges when supervised fine-tuning induces what researchers call pseudo-reasoning paths. When you force a model to mimic specific step-by-step examples during the initial training phase, it learns to imitate rigid structures rather than developing genuine understanding of the problem space. The model becomes hesitant and verbose because it is reproducing patterns from its training data instead of exploring optimal solutions on its own. This behavior creates inefficient trajectories where the model takes unnecessary intermediate steps just to satisfy the format constraints it learned during supervised fine-tuning. These redundant tokens are not just noise in the output. They represent a massive waste of computational resources that only becomes apparent when you try to move into the reinforcement learning phase. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Because of these imitative patterns, your GPU utilization suffers significantly during the subsequent reinforcement training stage. The hardware must process all those extra intermediate tokens generated by the pseudo-reasoning paths just to correct errors and find better solutions later on. This forces a scenario where memory bandwidth consumption spikes because the system is constantly shuffling data for steps that do not contribute meaningfully to solving the problem. You end up with a situation where your compute budget is spent correcting artifacts of supervised fine-tuning rather than exploring new reasoning strategies. The signal-to-noise ratio degrades, and you need significantly higher compute budgets just to achieve convergence on complex tasks compared to models trained differently from the start. Now consider what happens when you flip that script entirely and rely primarily on reinforcement learning methods like group relative policy optimization without a heavy supervised fine-tuning phase first. In this approach, the model is not trying to imitate rigid step-by-step examples, but is instead optimizing directly for correct final answers through trial and error. This method fosters authentic reasoning patterns that squeeze inference trajectories by eliminating redundant steps entirely. The result is a dramatic reduction in memory bandwidth pressure because the system does not need to process unnecessary intermediate tokens during either training or deployment. Models trained this way can achieve state-of-the-art performance on reasoning leaderboards with fewer computational resources than their SFT-heavy counterparts. This leads us to the critical insight that changes how you should approach hardware architecture selection for these models. The choice between supervised fine-tuning and reinforcement learning is fundamentally a constraint on your GPU utilization strategy rather than just a question of which algorithm produces better accuracy metrics. When you prioritize supervised fine-tuning, you are locking yourself into workflows that require memory bandwidth optimization for long, verbose context windows because the model will naturally generate more tokens per query. Conversely, when you lean heavily into reinforcement learning, your hardware priorities shift entirely toward compute density and high-throughput trajectory compression since the reasoning paths become shorter and more direct. The hidden tax of the traditional SFT then RL pipeline is a lock-in effect, where the rigid patterns learned during initial training degrade the efficiency signals needed for effective reinforcement learning later on. Practitioners working with models like VLAA Thinker have reported that bypassing supervised fine-tuning allows them to squeeze inference time significantly more effectively than standard pipelines allow. This suggests that the traditional method imposes a hardware tax where you pay twice in terms of compute cycles, once during inefficient supervised training, and again when your GPU struggles to correct those imitative patterns during reinforcement learning. The trade-off involves balancing initial SFT training costs against long-term inference savings, but current data focuses heavily on final accuracy rather than granular metrics like memory bandwidth usage across different batch sizes. This shift in perspective means that for production environments where you need format compliance and stable outputs, supervised fine-tuning still serves a necessary role as an expansion phase to stabilize model behavior. However, the decision of how much weight to give that initial phase should be dictated by your specific hardware constraints rather than academic dogma about training best practices. If your goal is maximum efficiency on limited GPU resources, or you need high-throughput inference for real-time applications, minimizing supervised fine-tuning and maximizing reinforcement learning might yield better total system performance despite the higher risk of format errors during early deployment stages. The key is recognizing that every token generated by a model trained with heavy imitation patterns represents a physical cost in terms of memory access and compute cycles that could be avoided entirely through different training strategies. Understanding this hardware efficiency constraint allows you to make more informed decisions about your engineering stack as an early career software engineer building production-grade systems. You are no longer just choosing between two algorithms, but selecting between two fundamentally different utilization profiles for your physical infrastructure. The future of reasoning models lies in optimizing these trade-offs based on the specific constraints of your deployment environment rather than following a one-size-fits-all training pipeline that ignores the physical realities of GPU memory and bandwidth limitations. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.